Welcome to The Explainer. Today, we're going to look closely at something truly fascinating, the realization that biological life isn't magic. Stop and think for a second about the sheer scale of what's happening inside your body right at this exact moment. From the coordinating beating of your heart to the incredibly precise way a life-saving drug finds its exact target out of trillions of cells, it's all a highly orchestrated dance of predictable molecular forces. We're going to completely unpack the invisible rules that dictate how you are alive. Okay. Here is our roadmap for today. We'll start with the energetic rules, move into types of molecular bonds, discuss water and the environment, dive into pharmacodynamics, look at enzymes and crowding, and wrap it all up with the clinical checklist. Let's jump right into Section 1, the energetic rules, the absolute foundation of biological interactions. To really understand how our bodies and the medicines we put into them actually work, we have to start with the ultimate energetic driver of, well, absolutely everything. The crucial thing to remember here is that molecules are not acting randomly. They don't have a conscious plan, and they certainly don't have tiny brains guiding them to where they need to go. No, they are strictly governed by thermodynamics, specifically the unrelenting drive toward the lowest Gibbs free energy state. That's delta G equals delta H minus T delta S. This is the law that dictates every single interaction in the universe. It balances enthalpy, which is the heat or energy locked in the bonds, against entropy, which is the amount of fundamental disorder in a system. Honestly, biology is essentially a constant pursuit of thermodynamic laziness. For any biological event to happen, whether that's a neurotransmitter firing a signal across a synapse or a drug successfully binding to a cancer cell, it absolutely must result in the universe seeking a more disordered, lower energy resting state. Moving on to Section 2. Types of molecular bonds, the actual building blocks of life. So, how does nature actually build interactions to satisfy those energetic rules we just talked about? Well, there's a massive, essential difference between the two main categories of interactions here. First, you've got permanent structural bonds. These are your covalent bonds, where electron pairs are literally shared between atoms. But then, you have non-covalent forces. These are weaker, and critically, they are completely reversible. Now, this reversibility, it is the actual secret to life. Think about it for a second. If drugs or cellular signals were strictly covalent and permanent, every time a molecule bumped into another one, it would get permanently stuck. Your biology would just instantly freeze solid. So while covalent bonds build the rigid skeleton of your molecules and the solid backbone of your DNA, it's the non-covalent, reversible forces that act as the dynamic, ongoing conversations happening between your cells right now. Look at the sheer difference in power here. We're comparing the massive energy of a permanent covalent bond, clocking in at up to 800 kilojoules per mole, all the way down to the incredibly weak temporary van der Waals forces at the bottom of the spectrum, which sit between roughly 0.4 and 4 kilojoules per mole. As you move down this list from covalent to ionic, then to hydrogen bonds, and finally down to van der Waals, you transition from permanent, rigid structure to highly dynamic interaction. Sure, those weaker forces might look statistically insignificant by the numbers, but here's the catch. When you add millions of them all together in a three-dimensional space, they act as the highly precise software code that seamlessly runs the human body. In fact, even the weakest forces on that list have profound clinical realities. Let's unpack how salt bridges, which are a type of ionic bond, actually stabilize the shifting structural states of hemoglobin. As your blood circulates, these salt bridges are rapidly forming and breaking, physically altering the shape of the hemoglobin protein so it can seamlessly pick up and drop off oxygen. Without that specific reversible bond, you literally couldn't breathe. Then you have hydrogen bonds, which are incredibly directional. Picture your DNA double helix being perfectly zipped together by millions of these hydrogen bonds. They create this unyielding zipper effect, ensuring absolute genetic fidelity every single time a cell divides. And what about those tiny van der Waals forces? They dictate steric hindrance. That means they physically prevent drug molecules from awkwardly clashing into cellular receptor pockets where they just don't belong. Which brings us to Section 3, water and the environment. It's the ultimate active participant. None of these molecular bonds happen in a vacuum, which brings us to the number 80. This is water's dielectric constant, and let me tell you, it is a massive factor in biochemistry. Water is highly polar. It has a partial positive charge on one end and a partial negative charge on the other. Because of this dual nature, water aggressively pulls apart exposed ionic bonds. It acts almost like a molecular solvent that forces proteins to hide their sensitive, charged structures. Because water's dielectric constant is so incredibly high at 80, proteins are literally forced to bury their strong salt bridges deep inside their completely dry, hydrophobic cores just to protect them from the water surrounding them. And that dynamic builds into arguably the most important force in all of medicine, the hydrophobic effect. Interestingly enough, this isn't even technically a bond. Nonpolar molecules, like fats, absolutely cannot form hydrogen bonds with water. So water molecules respond by forming a highly ordered cage, called a clathrate, around the fat. But here is the deep explanation of why this actually matters. Water molecules desperately want to dance freely. Locking them into a rigid cage around a fat molecule severely drops the system's entropy, which, as we established back in Section 1, thermodynamics strictly forbids. To minimize this rigid water cage and let the water move freely again, nonpolar substances are essentially forced to cluster tightly together simply to get out of the way. This single entropy-driven effect is what creates your cell membranes and dictates how every single protein in your body folds. When this process fails and sticky hydrophobic patches are left exposed, it leads directly to catastrophic conditions like Alzheimer's and prion diseases. And while we're talking about the cellular environment, we have to clear up a very common misconception. It's a mistake to think cells are mostly empty, watery balloons. They are incredibly packed. The high concentration of macromolecules inside a cell drastically limits the available space. Think of it like trying to fully unfold a gigantic old-school paper map inside a densely packed subway car during rush hour. You just can't do it. This physical volume exclusion actually favors protein folding because there literally isn't enough physical room for proteins to exist in large, floppy, disordered states. All right, let's head into Section 4, pharmacodynamics, or drug binding in action. Let's transition into how doctors and pharmacologists use these invisible interactions to explain drug affinity and specificity. Now, we used to conceptually describe drug binding using this outdated lock and key model. It assumed both the drug and the target receptor were perfectly rigid puzzle pieces that just slid seamlessly together. But the modern, accurate model, it's called induced fit. When a drug approaches its target, initial weak interactions, like a few of those hydrogen bonds or van der Waals forces we mentioned, actually cause the receptor to physically reshape and tightly wrap around the drug. As the receptor changes shape, it forcefully displaces highly ordered water molecules out of the binding pocket and back into the main cellular fluid, just like we talked about with the hydrophobic effect. This displacement creates a massive burst of entropy, instantly satisfying the laws of thermodynamics and solidifying a tight, highly effective bind. Okay, so with all these invisible thermodynamic forces and the constant displacement of water molecules at play, you might naturally be wondering, how on earth can we actually quantify a given drug's effectiveness in the human body? Well, we measure this using something called the dissociation constant, or KD. This number represents binding affinity, and the inverse relationship here is the crucial takeaway. A low KD indicates a very high affinity interaction, meaning the drug binds strongly and stays there. Let's ground this in reality for a second. If a newly developed drug has a KD in the millimolar range, it's practically useless. You would need to swallow literal handfuls of pills just to get a basic therapeutic effect, which would inevitably cause massive systemic side effects. However, if a highly potent drug has a KD down in the nanomolar range, a tiny, microscopic dose is all you need for the drug to perfectly lock onto its target. Next up is Section 5, enzymes and crowding, the true dynamics of metabolism. Just as drugs have a KD, enzymes have something called the Michaelis constant, or Km. Now, it's absolutely important to explicitly differentiate these two ideas. While KD measures the passive, static binding of a drug to a receptor, Km measures the active, dynamic process of an enzyme grabbing onto and physically chewing up a biological substrate. A low Km means the enzyme is highly sensitive. It has incredible affinity and will snatch up substrates even when their concentration in the blood is extremely low. Understanding this Km value is vital for making sense of everything from basic human metabolism to diagnosing really complex toxicology cases in the emergency room. This naturally brings us to competitive inhibition, which is exactly how life-saving drugs, like statins for high cholesterol, actually lower your lipid levels. Think of the statin molecule as a molecular imposter. First, this imposter drug is perfectly designed to chemically mimic your body's natural substrate. Second, it sneaks in and binds to the enzyme's active site using those dynamic non-covalent forces we discussed earlier. Because the drug and the natural substrate are competing for the exact same spot, the apparent Km increases. That just means it now takes way more natural substrate to achieve the same metabolic rate. But here's the trick. The maximum velocity, or Vmax, remains exactly the same. Why? Because if you simply flood the system with enough natural substrate, it will eventually overwhelm and completely outcompete the imposter drug. And this perfectly illustrates two beautifully complex concepts: cooperativity and allostery. Often, a molecular interaction at one specific site on a protein physically influences interactions at a completely different, distant site on that exact same protein. Let's look back at hemoglobin. When just one single oxygen molecule binds to it in your lungs, it pulls the protein's internal iron atom by just a tiny fraction of an angstrom. Seriously, it's microscopic. But that incredibly tiny tug ripples across the entire protein structure. It physically shifts the non-covalent salt bridges throughout the whole complex, instantly increasing the binding affinity of the remaining empty oxygen sites. This deep internal communication results in the famous sigmoidal S-shaped oxygen curve, and that curve guarantees efficient loading of oxygen in your lungs and rapid, essential unloading in the deep tissues that desperately need it. Finally, Section 6, the clinical checklist. This is where we apply the molecular mindset. Whenever you're evaluating a clinical condition or even conceptualizing a new medication at the microscopic level, these are the fundamental questions you have to ask to connect pure thermodynamics to real-world pharmacology. First, is the interaction reversible? Second, is it driven by hydrogen bonds or the hydrophobic effect? For example, if a drug needs to cross the blood-brain barrier to treat a neurological condition, it strictly requires a hydrophobic nature to smoothly pass through that specialized fatty barrier. And finally, what is the dissociation constant, or KD? Does it bind tightly enough to work effectively at a wonderfully low dose, or does it bind so tightly that it becomes a dangerous, toxic liability? And on that critical note of toxicity, here's a stark reality check. Remember that while most successful drug interactions are beautifully, elegantly reversible, accidental covalent bonds can be completely fatal. Organophosphate poisoning, which often results from exposure to harsh agricultural pesticides, acts as an irreversible suicide inhibitor. It forms a permanent, incredibly strong covalent bond with critical enzymes in the human nervous system. Because that single covalent bond contains up to 800 kilojoules of energy, the body's normal physiological processes literally do not have the biological force required to pry the pesticide off the enzyme. It shuts the nervous system down permanently simply because the body cannot reverse the energy state. So, what precise balance of molecular forces is keeping you alive right now? I'll leave you with that provocative thought. After breaking down the thermodynamic equations, the thousands of tiny reversible bonds making real-time microscopic decisions, and the invisible, chaotic displacement of water molecules inside your jam-packed cells, I really hope you now view every single breath you take and every beat of your heart as a miraculous, perfectly balanced chemical equation. Keep questioning the invisible forces around you.